Hello and welcome to episode 5 of the Science and Maths discussion. And today we'll be discussing our favourite maths problems and puzzles. They won't include any long maths working out, but rather logic and quick creative thinking. Let's get into it. There we go.
Okay, so the first problem is from the Brilliant.com daily challenge, and this is based on chests. There are two chests. One contains gold, and each chest, let's call them A and B, has a statement based around them, and one or both of these statements are false. And you need to find out which chest contains gold.
I think I remember
So
this one actually. I think I did this.
Yeah.
It's a good one. It's great.
So chest A, there is gold. The statement is gold is in this chest, and for chest B, gold is not in this chest. So one of or both of those statements are false. So if they must be both false because in any other configuration they're contradictory. For example, if the statement around A is false, which is gold is in this chest, i.e., gold can't be in chest A, then and chest B's statement is true, where gold is not in this chest, then gold can't be in either of the chests. So they're both false. For example, so gold is in chest A. Gold is not in chest A. Gold is in chest B. So gold must be in B. And following on from that one, I think it's an example question from that same kind of daily challenge. So this time there are three chests, and gold is in only one of them, and there are three statements to each of these chests, A, B, and C. One is true, and two are false. So for chest A, the statement is gold is not in here, and for chest B, the statement is gold is in chest A, and for statement C, gold is not in here. So you need to look at which statements are about one particular thing. So statements A are A, which is gold is not in chest A, and B, gold is in chest A, are both about chest A, so they're contradictory, so cannot both be true or false, because otherwise it would just be impossible. And also, A and C cannot both be false, which are A, gold is not in chest A, and C, gold is not in chest C, since you would need two sets of gold, because then gold would have to be in both of them, where there is and in the problem you're only allowed one set of gold. So therefore A is true, and C is false. So B must also be false because there's one true and two false, and therefore the gold is in C, since it is false and it states that gold is not in here, which means it must be in there.
Nice.
Yeah, that's it.
I've got another brilliant daily challenge from the 22nd of the 8th of the 2021 called Keys Speed is the Key. It says that Clara left the house and realised that she forgot her keys. She asked her sister Daria to throw them from the balcony at 6 meters above the ground. Daria threw them straight down with initial speed 15 meters per second. Assuming gravitational acceleration g equals 10 meters per second squared, and neglecting air resistance, what is the approximate speed of the keys when they reach the ground? So we have some keys, we don't know their mass, being thrown from 6 meters, initial velocity of 15 meters per second. And we have to find the velocity they have at the ground. We can calculate their energy using both the equation for gravitational potential energy and for kinetic energy, and by adding these together. So the gravitational potential energy, being 6 meters above the ground, mgh, mass, we don't know, but gravitational acceleration is 10, and height is 6 meters. So we can write that, and we know the velocity is 15 meters per second, so we can work out the energy that way. We can write. So we know both these equations, and they're very useful to do this. There's a very good way, because we don't know the mass, so that can make things confusing. We can write the energy at the start is going to be all transferred to velocity at the end, and that's what we want to know when it hits the ground. So we can write a little equation that the gravitational potential energy plus the velocity at the start is equal to the velocity at the end. So mgh at the start, when it's 6 meters high, plus the energy of having 15 meters per second, a half mv squared, where v is 15, equals half mv squared, where v squared v is the final velocity we want to know. And this is useful because we can get rid of mass cancels out, and we find velocity to be equal to 18. It's a very sort of common sort of question. You'll see a lot of these exchanging between velocity and gravitational potential energy, kinetic energy, sorry, instead of velocity. But you'll see a lot of these, and it's quite intriguing. It's good. It's a good way. It's a good practice. Will, the next one.
Yeah. So this is again from a brilliant.
They're so good. They are really good. I would recommend
Yeah.
getting to them if you haven't been.
They explain them very well.
They do,
So,
yeah.
there is a sum of 5 plus 5 plus 5 plus 5, so 4 fives all added together, and you're allowed to change any of the signs to any other sign, so minus, division, multiplication.
Yeah, I did this one as well. It was great. I
Yeah.
like this one.
And how many primes can you create from that sum if you change the signs? So to do this, I think it's useful to kind of look at what the effect of changing any of the signs would be. So if you just leave it as default with addition, then it's always going to be not a prime, since 5 plus 5 plus 5 is divisible by 5, and so if you change it to subtraction, that if you change 1 to subtraction, then 5 minus 5 is just 0, so you just kind of take out that facet of the problem, and it's still divisible by 5 and 2, because it's just 5 plus 5 equals 10. And if you change to multiplication, then it's always going to be divisible by whatever you're multiplying by. So the only sign that actually works is division, where you can change. So if you added 1 division sign anywhere in the problem, then you could change some like part of that sum to 1, which would be helpful. So for example, if you have 1 division sign, 5 plus 5 plus 5 divided by 5, so 5 plus 5 is 10, 5 divided by 5 is 1, and then you add them together, that equals 11, which is obviously a prime number. And then if you add 2 divisions, for example, 5 divided by 5, in the configuration, 5 divided by 5 plus 5 divided by 5, that equals 2, which is another prime number. Although you can't actually go the full distance and have 3 divisions, because that would be like weird fractions. So yeah, the answer is 2 primes can be the sum of this problem.
Yeah. I've got another one. Junior Mathematical Challenge 1999, question 7. This isn't a particularly hard problem in any way. It's just sort of a format you're going to see all over the place, and it's a very simple entry one to make it feel simple in your mind. I know that I've seen a lot of them like this, and I get confused. Anyway, so Mary has 3 brothers and 4 sisters. If they and Mary all buy each other an Easter egg, how many Easter eggs will be bought? This is, very easy, but it gets people. They like to use this format and get more complicated, so it's good to have a basic understanding of it. So there are 8 siblings. They all buy 7 eggs. So 8 times 7 equals 56. There we go. It wasn't complex math to explain out loud, but it's a good one. It's something you'll see a lot, and it's good to practice a lot of these basic ones where you have large numbers of things each interacting with each other in a certain way. Right, next one, Will. I know that was a quick one.
Yeah. So I mean, this one's again from Brilliant Daily.
They're just too good, aren't they? They're just too good.
Yeah. Well, all of mine are. So this is quite a simple one as well. So it's there are 2 water containers, one with 2
Yeah,
liters.
I like this one. So
Yeah,
I love Brilliant.
So this one has 2 liters and one has 6 liter has a 6 liter capacity, and there are 3 actions that you can take based around these. two containers. So one is you could fill a container to the top fully, so you can't like fill it like halfway or whatever. Another is you could pour the water directly, just pour all of the water onto the ground, so empty out the container. Or you could also pour water from one container into the other container until it is empty or the other is full. And the question is, how many different total amounts of water can be measured? So first let's get the obvious ones out of the way. You can obviously measure 2 litres from the 2 litre container, 6 litres from the 6 litre container, and 8 litres from measuring out 2 litres and 6 litres. A bit more complex. If you empty the small container into the big one, it's always going to be a multiple of 2, because you're just adding in increments of 2 because it's a 2 litre container. So you can have any value from 2 to 8, since you can just fill gradually and then fill the 2 litre container itself. And we've already got 2, 6 and 8, so the last outlying value is 4 litres, which you accomplish if you fill up the 2 litre container, pour it in to the 6 litre, and then fill it up again and do the same to have a total of 4 litres. And therefore you can measure 4 different values in total. Yeah.
Cool, nice. The next one I've got is some Intermediate Mathematical Challenge 2001 question 15. You're given 5 numbers, and you're asked how many of the following numbers are greater than 10. The numbers are 3 times the square root of 11, 4 times the square root of 7, 5 times the square root of 5, 6 times the square root of 3, and 7 times root 2. So this requires a basic understanding of surds, which is the understanding of root numbers. And the idea being greater than 10. So the number has to be greater than the square root of 100, because that is 10. That's going to become very useful. So this is how we're going to solve it. We're given the number 3 times the square root of 11. This can also be written as the square root of 9 times the square root of 11, because the square root of 9 is equal to 3. And when you have two of these square roots together, square root of 9 times square root of 11, you can sort of times them together under one big square root to become square root of 99. And square root of 99 is smaller than square root of 100, therefore 3 times the root times root 11 is smaller than 10. So that's just a fun little thing. I'll do it for the others as well. 4 times square root of 7, which is the square root of 16 times the square root of 7. And you times that together under one big square root, and you get square root of 112, which is greater than square root of 100, which therefore is greater than 10. Again, 5 times the square root of 5, square root of 25 times the square root of 5, square root of 125, greater than square root of 100, greater than 10. And you'll find the other two, 6 times the square root of 3 is greater than 10, and 7 times the square root of 2 is less than 10. Therefore, 3 out of the 5 numbers are greater than 10. It's an interesting problem, and the idea of timesing surds together is very important, and you'll find that everywhere. Right, back to you, Will.
Okay, so this is my final one, and it's also from Brilliant. Daily challenges. They're the real MVP of this.
I want to see if I've done it as well, so I've seen if I can do all of them. Anyway, carry
on. So you pick a random number, and there's a 2-digit random number positive, and there are 4 possibilities of what it could be. Well, there's more, but these are the ones specified in the thing. So either the number is divisible by 10, the number is divisible by 2 and 5, C, the number is divisible by 2 but not 5, and D, the number is divisible by 5 but not 2. And you have to find out which is, there 3 are equally likely and 1 is more likely than all of the others, and you have to find out which one it is. So I think although they're 2-digit numbers, there's obviously not 90 from 10 to 99. But you don't really have to go through all of them to find out which one's the most likely. So what I did is I cut it down to a sample size of one kind of decade of numbers, so 10 to 19, and from that you can get a basic idea of the probabilities. So for example, in the decade of 10 to 19, there is only one number divisible by 10, which is obviously 10, and there is also only one number divisible by 2 and 5, which is also 10. And then there are actually four, if you go through it, there are four numbers divisible by 2 and not 5. So that's 12, 14, 16, 18. And there's only one number divisible by 5 but not 2, which is 15. Therefore, the statement C, numbers divisible by 2 and not 5, is most likely to be fulfilled. Which actually, well, it makes a lot of sense, because any even number that is not divisible by 10 is obviously going to be divisible by 2 and not 5. So, yeah, so C is the most likely.
Nice, yeah, I like that one. Here's my final one as well. Teams Maths Challenge Regional Finals 2009 Relay A14. Catchy. I have an unfair dice that's probability 1/2 of landing on a 6, with the other numbers equally likely. If the dice is thrown twice, what is the probability of obtaining a total score of 10? So, to do this, we look at how we can get 10. We can get 6 and 4, 4 and 6, and 5 and 5. So to get 6, we have a 50% chance, or a 0.5 probability. So to get 6 and 4, we'll get a half times a tenth, because we have 5 other values that aren't 6 split into the other 50%. So they're all going to be 1/10 or 10%. So 6 and 4 will be a half times a tenth, which is a 20th. 4 and 6, it's just the other way around, it's also going to be a 20th. And 5 and 5, both of them being not 6, they're both going to be a 1/10 chance to be 1/10 times 1/10, which is 1/100th. So all these three possibilities work, so we can add up our probabilities for all of them. 1/100th plus 1/20th plus another 20th equals 0.11. We should always give probabilities from a number from 0 to 1, not as a fraction. So there we go. Our chance of getting a total score of 10 is 0.11. Nice little probability question. That's it. That's everything.
Yeah.
Cool.